students, last class we discussed about the formation of LC oscillation and the energy transformation during LC oscillations. How the LC oscillations are produced with a definite frequency, all these things are we discussed in the last lecture. Okay. Now we are going to discuss about conservation of energy in LC oscillations. During LC oscillations in the LC circuit, the energy oscillates back and forth between the electric field of the capacitor and the magnetic field of the inductor. So the energy oscillates back and forth. The energy continuously vary with respect to time. But one thing is, the energy changes from inductor to capacitor, capacitor to inductor. That is, energy transformation takes place with respect to time. But the total energy of the system remains constant. There is no change in the total energy of the system. So during LC oscillations, the energy may transfer from one component to another, capacitor to inductor, inductor to capacitor, we will agree, but the total energy of the system remains constant. That means this system obey law of conservation of energy. We now going to prove this law, this conservation of energy in LC oscillations by taking three different cases. In the case 1, look at the diagram. This is the diagram for case 1. In the case 1, here the capacitor is fully charged. So the charge in the capacitor is maximum, so we write Q is equal to Qm. In the circuit, the current passing through it is 0 because the capacitor having maximum charge. So no charge flows through the system, so no current will flow through the circuit, and the inductor's energy is 0 here. Now we are going to prove this. The total energy of the system is nothing but it is the sum of the electrical energy and magnetic energy. So U is equal to, what is the formula to find out electrostatic potential energy is Q square by 2C, and sorry, here we use small q, okay, Q square by 2C. Q square by 2Z, and the formula to find magnetic potential energy is half Li square. Okay, U is equal to Q. Here the charge is maximum, the capacitor stores maximum amount of charge in this case. So we write, instead of Q, we write Qm square by 2C plus half L, the current is 0 in this case, no current flows through the circuit. So the total energy at that instant is Qm square by 2C. Qm square by 2C. So Qm square by 2C is the total energy, which is nothing but that is only electrical energy. Only electrical energy is created in this situation, in this instant. There is only electrical energy. There is no magnetic potential energy here. So the total energy is wholly electrical in this case. This is first case. Okay. In the second case, this is the diagram for second case. That is case number 2. Here the capacitor is fully discharged. All the charges are going to the inductor. So the current passing through the inductor is maximum. So we are taking I is equal to Im, and the charge stored in the capacitor is 0 because no charge is stored in the capacitor. So here the magnetic potential energy is maximum because when the current passing through the inductor, it produces magnetic field. So the magnetic potential energy around the inductor is maximum. In the inductor is maximum. Okay, what will be the electrical energy of the capacitor is, here the electrical energy of the capacitor is 0 because no charge is stored in the capacitor. Now we can prove this situation. Here we take U is equal to UE. UE means what? Q square by 2C. Here Q is 0. So first I write Q square by 2C plus half Li square. Here Q is 0, so total 0, half L into I. Instead of I, we write Im square. Im square, this is square, okay. You know very well, Im equal to Qm into omega. This is one of the expression. So we substitute this expression for this place. So U is equal to 0 plus half L into Im square. Instead of Im square, we write Qm square into omega square. We know very well the resonant frequency omega is equal to 1 by root of LC. This is one of the most important expression we know. So omega equal to 1 by root of LC, omega square is equal to 1 by root of not root 1 by LC. If we put square, then the square root will be cut in the right hand side. So omega square is equal to 1 by LC. So I write here LC only. So here L and L get cancelled. The last term is QM square by, this 2 comes to down, that means denominator. So QM square by 2C here, QM square by 2C. Okay, yes. So look at these two final expression. In the first case, the total energy is wholly electrical. In the second case, the total energy is wholly magnetic. There is no electrical component. There is no electrical energy here in this case. But both of them having the same expression. That means the energy remains the constant. This is wholly electrical, okay. This is wholly magnetic, okay. But what is the total energy? The total energy of the two cases remains constant. We proved, okay. Now we are going to discuss about the third case. In the third case, here the diagram for the third case, here the capacitor begins to discharge. So part of the charge of the capacitor discharge, the remaining part of the charges are stored in the capacitor. So the capacitor is charged as well as capacitor is discharged. So some of the charges are going, so they produce current that is taken as I. Here the charge of the capacitor is Q, here the current flowing through the inductor is I. So inductor produces a magnetic field. So in this case, inductor has some magnetic potential energy, capacitor has some electrical potential energy, electrostatic potential energy. So both the energies are present in this case. Okay, in this case, both the energies, energy due to electric field, energy due to magnetic field, both the energies are present in this situation. In this case 3, we are now going to prove. Case 3rd. In the case 3, the total energy is equal to Q square by 2C, we know very well, Q square by 2C plus half L I square, okay. First, Q is equal to, we have to substitute two things. First one is Q is equal to, here, Qm cos omega t. This is the value expression for Q. We have to substitute here instead of small q. Second one is I. How we can find I? We can find the value of I with the help of Q. How? We know very well the rate of flow of charge. The rate of flow of charges constitute electrical current. dq by dt is equal to I. So I is equal to minus dq by dt. Why we are putting minus here? I will tell you. Please wait. So minus dq, d by dt of q. What is the value of q? d by dt of q. The value of q is qm cos omega t. Okay, qm cos omega t. So I is equal to minus d by dt of qm cos omega t. We differentiate, qm is constant, so we will take it out. d by dt of cos omega t gives minus omega sin omega t. Okay, minus omega sin omega t. This is the expression. Okay, after differentiation. So I is equal to minus of minus plus. So qm omega sin omega t. Okay. Why we are putting negative sign in this expression is I equal to minus dq by dt means as the time increases, the charge decreases. As the time increases, the charge decreases. So we denote negative sign in this expression. Don't forget, this is one of the most important thing. Okay. What I have done here is u equal to q square by 2c. We can substitute the value of q. Q is equal to qm cos omega t. That is one thing. By the help of this q, we can find the value of current. I equal to minus dq by dt. So is equal to minus d by dt of q. What is the value of q? Q equal to qm cos omega t. So I write the minus here. Qm is constant, which is taken out. The remaining term is d by dt of cos omega t. When we differentiate cos omega t, it will become minus omega sin omega t. So minus of minus, it becomes plus qm omega sin omega t. Okay, we can substitute these two terms in the above expression. This expression number 1. For example, this is taken as expression number 1. Then u is equal to qm, q square. Instead of q square, I can write qm square cos square omega t, yes, by 2c, okay, plus half L. Instead of I write this term. What is the value of I? Value of I is here q m omega sin omega t. So here I square, so q m square omega square sin square omega t. Yes, I write correctly. But we know omega square is equal to 1 by root of LC. Omega square is equal to 1 by LC. So instead of omega square, I substitute here 1 by LC. So here 1 by what else? Okay, here L and L are cancelled. So the remaining term is the first we should take the common term. The common term here is qm square by 2c. Qm square by 2c, which is taken out. The remaining term what is here? Cos square omega t. Cos square omega t is the term which remains. Cos square omega t plus here qm square by 2c is taken out. The remaining term is sin square omega t. Cos square omega t plus sin square omega t is equal to 1. We know very well. So the final expression becomes u is equal to qm square by 2c. Yes, because cos square omega t plus sin square omega t equal to 1. So look at the final expression for three different cases: qm square by 2c, qm square by 2c, qm square by 2c. So here the whole energy is only electrical, here the whole energy is only magnetic, here the whole energy is the combination of electrical and magnetic. So the energy of the system may oscillate between the electric field of the capacitor and the magnetic field of the inductor. It may oscillate. When the electric field is maximum, when the energy of the electric field is maximum, the energy of the magnetic field is 0. When the energy of the magnetic field is maximum, the energy of the electric field is 0. It may happens, okay, but the total energy of the system remains constant. In these three cases, we proved that the total energy of the system remains constant during the formation of the LC oscillations. This is what we have studied now. Okay, in this class we will discuss successfully about the conservation of energy in LC oscillations. Next in the next video we are going to discuss about a new topic. Okay, till that, bye my friends, bye my dear students. Thank you.